Hello, my name is Jessica Eberly, and I'm going to be discussing the paper on the molecular simulation of the DPPE lipid bilayer gel phase. This paper was written by Dr. Apollory, Dr. Kopic, and Dr. Kent, who performed these experiments in the Department of Chemistry at Emory University. First of all, it's important to develop a basic understanding of what this DPPE lipid bilayer is and what the gel phase means. We know from previous classes that the lipid bilayer is a thin membrane made of two layers of lipid molecules that form a continuous barrier around cells. We know that these are arranged in a way that the hydrophilic head groups are on the outside and the hydrophobic fatty acids are facing in. The DPPE portion of this lipid bilayer refers to the dipalmitoyl phosphatidylethanol that makes up the composition of these lipid bilayers that are in question in this paper. One of the most important properties of any lipid bilayer is the fluidity of the individual molecules and how their mobility interacts with changes such as changes in temperature. Under a broad scope, different temperatures can render given bilayers as either a liquid or a solid, with the solid phase being commonly known as the gel phase. Here on the left, we see a regular lipid bilayer. We see the hydrophilic head groups on the outside and the hydrophobic fatty acids facing in. The image on the right shows the transition from the gel phase into the liquid crystal phase. When it gets heated up, the molecules become more disorganized. The gel phase, again, just refers to it being in its solid state. This study specifically compares the effect of backbone order on the tilt in the gel phase of the DPPE bilayer using two different force fields, the Berger United Atom force field and the CHARMM-C36 force field, hereby known as CHARM-C36. When I say that this study compares the effect of backbone order on tail tilt, I mean that this study seeks to know what happens when the backbone is ordered. Will the tails be straight? Will they be tilted? It just seeks to understand the true correlation between the backbone order and the tail tilt. These force fields that are in question, the Berger United Atom and the CHARM-C36, are force fields that use functioning parameters to calculate the potential energy of a system. The Berger force field is a form of united atom parameters, which indicates that each hydrogen and carbon is treated as a single interaction center. The CHARM-C36 force field has been developed primarily for molecular dynamics that involve macromolecules. This force field considers all the coordinates of all the atoms within them as free variables. This study of the behavior of single-component lipid bilayers is beneficial for multiple reasons. The first is that the ability of a force field to represent the ordered phase is a measure of that field's accuracy. The better that a force field can represent the ordered phase, the more accurate that field is as a whole. Another important aspect of this is that by knowing the temperature at which there is a potential change for phase helps avoid unexpected effects when performing simulations that are near that particular temperature. When we know what temperature there's the potential for change, we know when to be more careful or when we should be expecting there to be a change in the form between the gel phase and the liquid crystal phase. And another important aspect is that understanding the structure and properties of the gel phase provides us with a deeper understanding of the behaviors of certain membrane systems. In order to determine the structure of the gel phase bilayer, the arrangement of lipids in the initial patch is important. This involved setting up either an ordered or disordered arrangement of sites on a triangular lattice. In this figure, each open blue circle is a lattice site, and each of these sites corresponds to the position of a lipid tail. The image on the left shows random backbone orientation with a hexagonal tail packing order. while the right image shows the difference in an ordered backbone pattern. Between each of these sites is a line. The red lines indicate bonds that maintain their original positions, and the magenta segments show the bonds that migrated during the procedure. The green segments are new bonds that were formed during the procedure, and the black segments indicate bonds that continue across the boundaries of the 20 by 20 lattice. This lattice structure was then converted into a lipid molecule configuration, and in order to avoid steric clashes between the lipids involved, these molecules were put into an expanded grid. After this was done, these layers, or leaflets, were placed with a gap between them, as shown in part A of this figure. This indicates an uncompressed or disordered structure. Image B shows the result of hydrating figure A and compressing them. When they compressed them, though, the Z dimension of the grid was fixed, and the X and Y dimensions were allowed to react to that compression. This allowed the lipids to become closely packed, though they don't show much tail tilt to the lipid tails. This represents the compressed but still disordered structure. Figure C is the image of a single lipid molecule. The yellow balls that are on each of the lipid tails indicate the C5 carbon of each, so you can see that the packing is normal. Figure D indicates the top view of this disordered structure, and figure E shows the compressed but ordered top view of a single leaflet. Both image D and E are colored so that the tail groups of the same molecule have the same coloring. So tail groups that have molecules that have two tails will have two of the same color dot beside each other. The simulations that use the Berger force field showed differences in their structural properties. This figure shows a profile of the gel fraction of the system, or the fraction of lipids within a 1 nanometer range of the X values, versus their position along the actual X-axis. These simulations produced these final structures from the Berger force field DPPE lipid bilayer that were equilibrated at 320 Kelvin from structures that were originally disordered on the top and ordered on the bottom. This figure shows that the systems with ordered backbones tend to get a distinct tilt in the lipid tails, though the disordered structure didn't show much tilt, only some curvature in the bilayer itself. This image shows the tail tilt angles in the ordered and disordered systems, respectively. The red indicates the top leaflets, and the blue indicates the bottom leaflets. This makes it exceedingly visible that the ordered bilayers had an increased tail tilt to that of the disordered bilayer, though the disordered bilayer shows a wider array on whether or not the tail does tilt. This figure shows the average amount of area taken up per lipid in the backbone. The blue line indicates disordered, and the red line indicates ordered backbones, showing that the system with the disordered backbone packs less densely as would be expected. This image shows the average tail tilt angle as produced by the Charm C36 force field. The red dotted curves show the tail tilt angle of the ordered backbone system, while all three of the solid lines indicate the disordered system. This again shows that there is a higher tail tilt angle in the ordered structure as compared to the disordered structure in the Berger force field simulations. This figure shows the area taken up per lipid as per the Charm C36 force field. The red dotted curve indicates the ordered backbone, and the other three curves show the disordered backbones. This again indicates the same thing as the Berger force field did, that the disordered system is less tightly packed than the ordered system is, which again is to be expected. Here, we see the cross-sectional views on the XZ plane on the left and the YZ plane on the right. These are the final structures of the DPPE bilayers after equilibration using the Charm C36 force field. The first image shows the backbone ordered set, and the lower three show the disordered structures. It's again worth noticing that the disordered structures show some waving within the bilayer itself, and the ordered backbone model indicates a much higher tendency towards tail tilt. The disordered structures show three versions that differ slightly. The first of the disordered backbones were allowed to develop on their own while there was still a gap between the leaflets. In P2 and P3, though, pressure was applied to the bilayer before tilt directions were allowed to form. This allows the conclusion that contact between the leaflets during the creation of the tilts doesn't necessarily determine the overall tilts within the leaflets themselves. The Berger simulation was shown to give an untilted gel phase, which is consistent with the experiment. When equilibrated at 5 different temperatures that were evenly spaced, definite growth was seen in the gel phase, as evidenced in this figure. This image shows the cross-sectional view of the alternating gel fluid phases of the system. The top image is the initial structure. The second structure is at 320 Kelvin, and the third is at 330 Kelvin. And you can see where the bilayer begins to spread as it alternates between the gel and fluid phase. You can really see in the second and third where the bilayer itself starts to spread out, creating a dip in the actual bilayer and moving apart the tails. As the width of the gel phase changes, the rate of its growth was assessed by a linear fit line. This compared the width of the growth to the time that it took. This is shown with all of the temperatures tested between 315 Kelvin and 335 Kelvin on the graph to the left. The graph to the right shows the growth of the gel phase domain width versus the temperature from the simulations as well, but with error bars shown. This investigation of the DPPE structures indicated that the tail tilt angle is sensitive to the ordering of the backbones. A disordered structure is less likely to have tail tilt, but more likely to have waves in the bilayer itself. An ordered structure is more likely to have tail tilts, but no waves in the backbone itself. It was also shown that an ordered backbone will be more compact, but have more tail tilt angles than that of the disordered backbones and vice versa. The overall conclusion shows that the computation modeling of gel phase structures should be initiated from a disordered structure rather than by the partial melting of crystalline packaged lipids that we currently use.